If you think this is a transistor, well, think again, because what you see here is just a plastic package. The funny thing about transistors is that, although they are everywhere, almost no one has actually seen one. Many engineers talk about transistors as being just an electrical switch, but that would be too simple, and engineers don't like simple things. So in this video, let's go beyond that and see what transistors really are, how they work, and why they are far more than just on and off switches. William Shockley once said, "The transistor is, by far, the most important invention of the 20th century." And that was in 1947, when his team at Bell Labs actually created the first bipolar transistor. Up to that moment, electronics relied on triodes, which looked like a light bulb but worked as a transistor and were really attractive for bugs. Before that, in 1925, Lilienfeld described the field effect transistor in theory, but was never able to build one, making him the only engineer in history to have documented things first. It was the job of two other engineers in 1960 to finally build the first practical FET and give birth to microelectronics. But how do they actually work? Bipolar junction transistors are based on two different silicon p-n junctions, which can be either PNP or NPN type. On one side, you have the emitter, which is heavily doped with impurities to provide majority carriers, which for the N-type are electrons. Then, the base is added to it, which is much thinner than the emitter and doped to be of the opposite polarity. Finally, the collector is added, doped with the same atoms as the emitter, but just lightly, which increases the voltage blocking capability of the transistor. Now, you wouldn't be wrong to say that this forms two diodes in opposite directions, but actually, it is more than that. Transistors just work the way they do because of two things: their thin base and their different doping strengths. Just like a diode, if you apply a certain voltage in the correct polarities, current will flow from base to emitter, with electrons migrating from emitter to base. But because the base is very thin, just a few electrons reach the base terminal. Most of them get caught up by the electric field in the collector-base junction, accelerate and diffuse through that p-n junction, reaching the collector side and creating the collector current. The ratio between collector and base current is known as beta, which is an important parameter of bipolar transistors. The collector current only flows when there is a base current, and this is why bipolar transistors are referred to as current control devices. But before you get rich with this knowledge, there's one thing you need to know. Bipolar transistors make less than 1% of all transistors out there, because modern microprocessors actually use FETs. Although also made of PNP and NPN junctions, FETs work in a very different way. On FETs, both source and drain are heavily doped. The layer in between, which is doped with the opposite polarity, is called body. Just like on bipolar transistors, this structure also forms two diodes. On the body surface, between drain and source, an insulation layer is created, and the gate is placed on top of it, forming a capacitor between gate and body. When a voltage is applied to this capacitor, the electric field pulls charges very close to the insulator, forming a thin conductive channel through the concentration of these charges. This channel gets stronger with high gate body voltages, reducing the resistance between drain and source and allowing current to flow for as long as the field is maintained. Because the gate is isolated, currents only flow on the gate terminal to charge and discharge this capacitance, and therefore FETs are referred to as voltage control devices. But you probably never saw a FET with 4 terminals. That's because in most cases, body terminal is connected to the source, simplifying its structure and allowing a voltage between gate and source to control the channel resistance. With that, one of the internal diodes is short-circuited, while the other one is left intact and is referred to as the FET's body diode. But transistors are like your girlfriend's past. The more you dig, the more you find out you don't know. Their different operating modes is what allows them to be more than just switches. Bipolar transistors can operate in 4 modes, depending on how their junctions are biased. In cutoff mode, the transistor is just blocking current. In active mode, linear current amplification takes place, like we saw before. In saturation mode, it is fully conducting, like a switch that is on. And in reverse active mode, where it also amplifies current, but is rarely used by anyone. FETs have 3 different modes depending on its gate and drain voltages. In cutoff mode, it also just blocks current. In linear or ohmic mode, it behaves like a variable resistor. And in saturation mode, it also acts like a switch turned on with a very low on resistance. Although each type displays dozens of different effects, typical applications have been established for decades and offer a good starting point on deciding which one to use. For instance, bipolar transistors are preferred for linear amplification or voltage regulation. That is because of their high current gain and greater linearity in analog operation. On the other hand, FETs are preferred when designing power converters and digital logic due to the high speed and lower current consumption. But if you really like to mix up things, I have good news for you. IGBTs combine the gate drive from FETs with the high current capability of bipolar transistors. These devices are more complex to build and typically found only on high power converter applications. All in all, transistors are in every electronic device that you have around you. If you'd like me to go deeper on the applications, let me know in the comments down below. And if you like this video, don't forget to like and subscribe to my channel and stay tuned for the ones to come. Thank you for watching and see you next time on Microprocessed.